Hello students, in this video we will discuss about Hess's law of constant heat summation. The energy changes accompanying chemical processes are governed by a general law or general principle known as this Hess's law. According to this law, Hess's law, the heat evolved or absorbed in a chemical reaction or a chemical process is same whether the process takes place in single or several steps under same conditions. Suppose in a process the system or a chemical substance or simply a system A changes to a system B, or simply a state of system of state A changes to a state B in one step, and the heat exchanged, it may be evolved or absorbed in this change is delta HR. Now suppose the system changes from the state A to B, state B in 3 steps involving a change from A to X, then X to Y, and finally Y to B. If delta H1, delta H2 and delta H3 are the heats exchanged in the first, second and third step respectively, then according to Hess's law, delta HR is equal to delta H1 plus delta H2 plus delta H3. Simply we can say that the heat evolved or absorbed in a chemical reaction or a process is same whether the process takes place in a single or several steps under same condition. Now let us take an example. Here the reaction carbon plus oxygen O2 gives CO2. The enthalpy change of that reaction delta H is equal to minus 393.5 kilojoule. Minus 393.5 kilojoule. Now this reaction carries out in 2 steps, in which one step is carbon plus half O2 gives carbon monoxide CO. Then the delta H of this reaction is minus 110.5 kilojoule. Similarly, this carbon monoxide again react with half oxygen, it will convert it to CO2 or it will convert it to CO2. Then the value of delta H is equal to minus 283.5 kilojoule. So this first reaction, that is carbon plus oxygen gives carbon dioxide. The delta H value is minus 393.5 kilojoule. This reaction may take place in 2 steps. First carbon monoxide is formed, then again it is converted to carbon dioxide. So first the formation of carbon monoxide, the value of delta H is equal to minus 110.5 kilojoule. Similarly, the second step, that is carbon monoxide plus half O2 gives CO2. The delta H value of this second step reaction is minus 283.0 kilojoule. Then we add these two enthalpy change values, we get this minus 393.5 kilojoule. So the enthalpy change of a particular reaction is always constant, whether it takes place in a single step or whether it is takes place in several steps. So simply we can say that the enthalpy change of a particular reaction is always constant and is independent of the path or manner by which the reaction takes place. So this generalization means in effect that the enthalpy of reaction depends only on the initial reactants and final products and not at all on the intermediate products that may be formed. It is also independent of path or the manner in which the change is brought about. Next, applications of this SS law. Applications of SS law. First one, this enthalpy change in a physical change or enthalpy change in a physical process. Example, enthalpies of allotropic transformations. Here consider this allotropic transformation of carbon diamond to carbon graphite. Carbon diamond to carbon graphite. The enthalpies of this transformation, that is carbon diamond to carbon graphite, which cannot be directly determined. It can be calculated or determined from the enthalpies of combustion of this graphite and enthalpies of combustion of diamond. This enthalpy of combustion of graphite, that is C plus O2 gives CO2. This delta H value is minus 393.5 kilojoule. Similarly, enthalpy of combustion of this diamond C plus O2 gives CO2, delta H is equal to minus 394.4 kilojoule. Then this equation, these two equations, that is this enthalpy of this combustion of graphite and combustion of this diamond can be taken as two equations, that is equation 1 and equation 2. Then equation 2 minus equation 1, when we subtract equation 2, equation 1, when we subtract equation 2 and equation 1, then we get carbon diamond, carbon graphite. The delta H value is equal to minus 1.9 kilojoule. Minus 1.9 kilojoule. Or we can get the enthalpy of combustion of carbon diamond to enthalpy of transformation of this carbon diamond to carbon graphite, simply subtracting equation 1 from equation 2. We can get this this enthalpy value minus 1.9 kilojoule. So Hess's law, from this Hess's law, thermochemical equations can be added, subtracted and multiplied or divided with suitable numbers, just like algebraic calculations. As a consequence, from other experimental thermochemical data, it is possible to calculate the heat changes of various reactions which cannot be experimentally determined. Then second application is enthalpy of formation. Enthalpy of formation. The enthalpy of formation of compounds can be calculated by the application of this Hess's law when it is not possible to determine experimentally. For example, it is impossible to determine experimentally the enthalpy of formation of this benzene from its elements carbon and hydrogen. However, it can be calculated from the enthalpy of combustion of benzene and enthalpy of formation of water and enthalpy of formation of carbon dioxide. From that values we can calculate or we can easily determine the enthalpy of formation of this benzene. So this is the equation for formation of benzene. 6C plus 3H2 gives C6H6, that is benzene. Now let us check how can we calculate this enthalpy of formation of this benzene C6H6. Here first one, C plus O2 gives CO2. Carbon plus O2 gives carbon dioxide. Delta H1, take it as delta H1. That value is minus 393.5 kilojoule. Take it as equation number 1. Similarly, H2 plus half O2 gives H2O. The enthalpy of that enthalpy change of that reaction is equal to minus 285.8 kilojoule. Take it as equation 2. And third one, enthalpy of combustion of this benzene, that is C6H6 plus 15 by 2 O2 gives 6 CO2 plus 3 H2O. The enthalpy of enthalpy value is delta H3 is equal to minus 3267.7 kilojoule. That is, take it as equation number 3. Sorry, here this equation number 3. This is equation number 3. Equation number 3. Equation number 3. Then multiply to this first equation, this C plus O2 gives CO2. This reaction is simply multiplied by number 6. We get 6C plus 6O2 gives 6 CO2. Then delta H value changes from minus 393.5 kilojoule to minus 2361 kilojoule. It's simply multiplied by 6. So we can get another equation number 4. Similarly, reaction 2 is multiplied by this 3, number 3. We get 3H2 plus 3 by 2 O2 gives 3H2O. And the enthalpy value is minus 887.4 kilojoule. This is equation number 5. Then we add this equation 4 and 5. We get another equation 6C plus 3H2 plus 15 by 2 O2 gives 6 CO2 plus 3H2O. And the value is the add value is minus 3201 minus 3218 plus 18.4 minus 3218.4 kilojoule. Take it as equation number 6. Then simply equation subtraction takes us equation 6 minus equation 3. We get this 6C plus 3H2 gives C6H6. That is the enthalpy of formation of this reaction is equal to 49.3 kilojoule. Similarly, we can calculate any enthalpy of formation of enthalpy of formation, and which cannot be determined by other method, or which cannot be determined directly. Then next, Kirchhoff's equation. Here first, the enthalpy or variation of enthalpy of reaction with temperature is generally expressed by this equation, Kirchhoff equation. The enthalpy change of any process, whether it is physical or chemical, varies with temperature. The exact influence of temperature can be understood by this Kirchhoff's equation. Here, consider a general reaction. Reactants gives products. Basically, this delta H is equal to sigma H of products minus sigma H of reactants, or the total enthalpy of products minus total enthalpy of reactants. Then dou delta H by dou T at constant pressure is equal to sigma of dou H products by dou T at constant pressure minus sigma of dou H reactant by dou T at constant pressure. This dou H by dou T at constant pressure is equal to Cp. This heat capacity. Dou H by dou T at constant pressure is equal to Cp. is already discussed in previous chapters. That is dou h by dou t at constant pressure is equal to Cp. Heat capacity. When it takes place at constant pressure, it is Cp. So here we can write it as dou delta h by dou t at constant pressure is equal to sigma of Cp products minus sigma Cp of reactants. So simply we can write it as dou delta h by dou t at constant pressure is equal to delta Cp. Cp, that is sum of heat capacities of products minus sum of heat capacities of reactants. So simply dou delta h by dou t at constant pressure is equal to delta Cp. Similarly, we can write it as dou delta U by dou t at constant volume is equal to delta Cv. Cv, or it is analogous lines. A similar equation can be derived from the temperature dependence of heat of reaction at constant volume. That is dou delta U by dou t at constant volume is equal to delta Cv. These two equations are known as Kirchhoff's equations. Similarly, when we integrate that two equations, here integrate from delta h1 to delta h2, delta h1 to delta h2 d delta h is equal to integral t1 to t2 delta Cp dt. We integrate this one, we can get this equation, delta h2 minus delta h1 is equal to delta Cp into t2 minus t1. Similarly, the another one, this equation, when we integrate this equation, we also get delta u2 minus delta u1 is equal to delta Cv into t2 minus t1. These two equations are known as integrated form of Kirchhoff's equation. Integrated forms of Kirchhoff's equation. But if however the temperature range is not small, that is, if it is desired to determine the enthalpy of reaction at a far higher temperature than the initial temperature, then constancy of heat capacities is no longer a valid assumption, and we must express the heat capacities as a function of temperature before carrying out the integration. So it is convenient to express the heat capacities as a power series in T, which is Cp is equal to alpha plus beta T plus gamma T square. This alpha beta are constants for a given species. Then this Cp, delta Cp changes to this delta alpha plus delta beta T plus delta gamma theta square plus dt. Then integrating that equation, we can get delta h2 minus delta h1 is equal to delta alpha into t2 minus t1 plus half into delta beta into t2 square minus t1 square plus 1 by 3 delta gamma into t2 cube minus t1 cube. This is the actual form of integrated Kirchhoff equation. So here this Cp changes to alpha plus beta t plus gamma t square. It is because when the temperature range is not small, it is desired to determine the enthalpy of reaction at a far higher temperature than the initial temperature, then the constancy of heat capacities is no longer a valid assumption, and we must express the heat capacities as a function of temperature before carrying out the integration. So it is convenient to express heat capacity as a power series of T. That's why we taken this one, Cp is equal to alpha plus beta T plus gamma T square. Then integrating this delta here, previous case here one delta Cp, this delta Cp. So here we get this delta Cp changes to delta alpha plus delta beta T plus delta gamma T square. And integrating this equation, we get the actual form of this integrated Kirchhoff equation. Delta H2 minus delta H1 is equal to delta alpha into T2 minus T1 plus half into delta beta into T2 square minus T1 square. Similarly, plus 1 by 3 into delta gamma into T2 cube minus T1 cube. So this is integrated Kirchhoff equation. It's actual form of integrated Kirchhoff equation.